Okay, we are almost everybody. Almost. Who's missing? Nobody. So, last time on Monday, more precisely, we were here. No, this is the next slide. So what now we will be talking about is well, we will show the global heat transport. As I told you before, the global heat transport is the current done by the current is keeping these differences between polar and equatorial regions constant, because there is a continuous lack of the energy received from the sun in the polar areas with respect to the equatorial area. So in order to keep these differences constant, there is this global heat transport by ocean currents and also by the atmosphere, because both the atmosphere and the ocean, they transport the heat between the polar equatorial areas and polar areas. And here is the global heat transport, but in the ocean, and expressed, presented for different oceans. And obviously there is a total heat transport in petawatts of heat. And what you can see is, for example, if you look at the specific ocean, I don't know, for example, for Atlantic, there is this northward transport, especially in the northern hemisphere. If you look at the Pacific, Ocean, this is this one thing here, and you can see that in the Southern Ocean you have the southward transport from the equatorial area toward the polar areas. In the northern hemisphere, you have the positive transport from the equator toward the polar areas. Obviously, it depends on the convention. What is positive? What is negative transport? Positive is northward, and negative is southward. But both of them represents the transport of heat between equatorial and polar areas. So if you do the sum of all these things, and obviously the Indian Ocean has only the southern component of this heat transport, because the Indian Ocean reaches only the equator and goes from the equator to the South Pole. So if you do the sum of all these, you obtain this curve, this S-like curve, which then really shows you how this transport is a function of latitude. So this is the total transport over all the ocean, and you can see clearly how this heat is redistributed within the Earth. Later on we will see what are the currents, the circulation in the ocean, which is taking care of this transport. What are the pattern of the circulation in the ocean, which is keeping this transport alive. And one of the things what we will be mentioning later on is that the climate change what we are facing right now will have as a consequence also of the changing of this meridional heat transport. So the equilibrium between equatorial and polar areas will not be as it is now, but it will change. It will change because the system of currents are changing, because they are changing the gradient of the temperature or density between different parts of the ocean. Here is something which explains to us to what extent and how the global mean temperature of the Earth's surface changes in the function of solar radiation. And this shows us to what extent these two things, solar activity and the temperature, how they are intimately related one to another. And a continuous line is the temperature, which is partly reconstructed from the proxies. It's not measured, and then part of it is the instrumental records, because we have instrumental records of the sea surface temperatures only in the last 200 years or something. So this part here is the mainly instrumental records. The other part is defined from different indicators of the sea surface temperature. And what you can see is this dotted curve is the solar activity, and they are very close to each other, except for some periods here and here. And I have to tell you also the dashed line here, this is the instrumental record, while the continuous lines is always the paleo reconstruction. And what you can see is that the two curves follow each other very, very nicely, except for some specific areas, like here and here. Why is this so? Here is mostly volcanic forcing, because there was a strong volcanic activity in the early 19th century, and this strong volcanic activity what caused the reduction of the sea surface of the Earth's temperature, Earth's surface temperature, because there was a huge amount of particles in the atmosphere which block this radiation, and therefore the sun, the relationship between solar activity and the temperature was different. And this is lower. The temperatures, Earth temperature was lower than it would be if we were looking only at the solar activity. On the other hand, the Earth temperature in the last 100 and 150 years is higher than it would be if we were looking only at the solar activity. Why is so? Because of the human activity, because of the anthropogenic influence, because of the climate change, because as I told you, as I mentioned you the day before yesterday, we are increasing the greenhouse gases, and we are really increasing the sea surface temperature over what would be if we were having the same influence of the sun as it used to be before. So these are another indications how the state of the atmosphere, either because of the particles or because of the presence of the greenhouse gases, could change the Earth temperature in a function of whatever is happening in the atmosphere. Because atmosphere absorbs part of this solar energy in a function to what is the state of this atmosphere. Okay? So this is another interesting stuff. Okay, now we will pass to temperature, salinity, and density. We'll be coming back later on the wind, and which is equivalent. The wind is equivalent to the sea currents, and you feel the wind. You know that the wind is movement over what air masses as the same as the current, which are movement of water masses. And now let's go and see what are the state variables of the ocean water. First of all, obviously, we have the temperature, and it's important because variety of physical processes depends on temperature, and the unit of temperature, as you all know, is Kelvin. And usually the measurement of temperature using the absolute scale is rather difficult, and it is made by National Standards Laboratory. The absolute temperature are used to define the practical temperature scale based on temperature of a few fixed points in interpolating devices which are calibrated at the fixed points. Then we have in the ocean, we are using a lot of potential temperature. Potential temperature is the temperature what is defined as the temperature of a parcel of water at the sea surface after it has been raised from a certain depth to the sea surface. So what is adiabatically? What that means? That means that we are neglecting the influence of the pressure, because we have a particle at a certain depth, 2,000 meter depth, and there the particle has a certain temperature, Ec2 temperature. But if we bring this particle into the surface, it will increase its volume, and it will obviously change the temperature accordingly. And this temperature what the particle has at the surface is a potential temperature. So we are bringing we are able to compare different parts of the Earth ocean by looking at the potential temperature, which eliminates the influence of the pressure. Typically, the measurements of temperature are done with instruments that have an accuracy of millidegree. Obviously, this accuracy is very important because if you will see later, the differences in temperature between different parts of the ocean or between different depths, especially in large depths, is on the order of 10 to the minus 2 degrees. And therefore, this accuracy of millidegree is essential in order to distinguish between different water masses, between different parts of the world ocean, between different depths. So this is the temperature. And then there is a salinity. Salinity is, as it is defined originally, while the salinity was used to be determined by the chemical approach, is defined as the total amount of dissolved material in gram per kilogram of seawater when all the carbonate has been converted to oxide, the bromine and iodine, replaced by chlorine, and all organic matter completely oxidized. In the salinity of the seawater doesn't enter organic matter. You cannot, in salinity, you don't put the fishes or plankton. Salinity is only the inorganic part, but only this oxide, bromine, and iodine replaced by chlorine. So this is the definition, exact definition of the salinity. But it was found out, and this first original definition of salinity really means that at the very beginning of the oceanography, chloride in the seawater, but fortunately for us, it was found that the salinity is directly proportion of chlorine in seawater, and since the chlorine can be easily determined chemically, the salinity was redefined in terms of chlorinity. So that's the fortunate property of the salinity, that the salinity is linearly proportional to the chlorinity. And so by determining chemically, at least at once upon a time, determining the chlorinity, we were able to calculate by this simple relationship the salinity. So this is that's the very good property of the salinity. And salinity is obviously then based on conductivity, because the conductivity depends on the presence of ions in the seawater. Therefore, next step in determining the salinity was, after having used this chemical method, which was very long and complicated, and we start to use the conductivity definition of salinity, and which is defined in 1978, based exclusively on the relationship between the conductivity and salinity. And this was a huge step ahead with determining the salinity, because you put your instrument into the sea and you read directly the conductivity, instead of picking up the sample, water sample, do the chemical analysis and so forth. So the various definitions of salinity work well because the ratios of various ions in seawater are constantly independent of salinity. This is what it says here. And the relationship between conductivity and salinity has an accuracy about 3 parts per thousand. Its accuracy. So more or less the accuracy of both temperature and salinity is few parts per thousand, which is also another important accuracy in order to distinguish between different water masses. Because you will see later that the salinity changes between the different parts, for example, of the Mediterranean, on the order of 10 to the minus 1 or 10 to the minus 2, and this is essential. Then your accuracy has been on the order of 10 to the minus 3.
Excuse me, Professor.
Yes.
I don't understand very well the definition, the original definition of salinity.
No, not either me. No, tell me.
Why is it important to convert all the carbonate matter to oxide?
To oxide bromine, because the oxide bromine and iodine are the ions, okay? And so that's the thing, that you have the ionic equivalent part of the salt material in the seawater. And this then you are able to relate to the, then you all these 3 ions are you express in terms of the chlorinity, and then you are able to determine it by chemical methods or by the conductivity, because the conductivity is directly proportional to the number of ions in the ocean. In the seawater. Okay, so the third, we have now the density. The density is obviously the function of temperature, salinity, and pressure. Absolute density can only be measured in special laboratories with an accuracy of 4 parts per million. And in oceanography, we work with density relative to the density of pure water. Density of pure water is 1, at 4 degrees Celsius. And the density of seawater density is typically 1/27 kilogram per meter cubic. So it's like a 27 parts per thousand heavier than the pure water. And in oceanography, what we do, in order to not to take all these times 10, we define the density as you often see the density defined. The values of density is 27.5. 27.5 means that the seawater is 27.5 kilogram per meter cubic heavier than the fresh water, than the pure water. Potential density, again, we are now coming back to potential density, where we, from the equation of state, we use the potential temperature instead of a Ec2 temperature, and then we obtain the potential density, because the pressure obviously influences primarily the temperature, but then influences also the density. The deeper is our water parcel, the smaller is the density, simply, the higher is the density simply to the pressure of the water column above. And in order to avoid this, in order to eliminate this part, we use the potential temperature in order to get the density which doesn't contain the influence of the pressure. Potential temperature density is not useful for comparison of water masses at greater depth, at several kilometers, and since the relation between temperature, salinity, and density is not linear. It's not linear, you will see later. As a result, two water samples having the same density but different temperature and salinity at a depth of 4 kilometers can have noticeable different potential density. Because if you have a different density temperature relationship at the same depth, the density will not be the same, simply because of the fact that the relationship between temperature, salinity, and density is not linear. But we want to have for the same relationship between temperature and salinity, we want to have the same density. In order to avoid this, we define the density relative to 4,000 decibel, 4,000 meters, 4 kilometers, and then we avoid this huge difference in depth, where we calculate this potential temperature between 4,000 and surfaces, huge difference in depth. So we avoid this different potential density, although we have at a depth of 4 kilometers, for example. This is something what is also we can remember. It's not so essential, but you should know that. Now let's see, to have an idea what are the average temperature and density and salinity over the world ocean. If you calculate the volume, average volume temperature over the entire ocean, we got this number more or less. 3.5 degrees Celsius is the average temperature over the world ocean. So what that means? That means that major part of the ocean has very low temperatures. Although we are, the part of the ocean where we are in contact with, it has a rather large high temperature, 20, 10 degrees and so forth. But considering that most part of the ocean is 5,000 meters deep, the average depth of the ocean, the temperature is relatively low, because 5,000 meter depth of the world ocean has a temperature around 4 to 5 degrees.
Which temperature is it?
Excuse me?
Is it real temperature or?
Real, that's a real temperature.
Potential.
That's a real temperature. That's a real temperature. And the mean salinity is 34.7 kilogram per kilogram. So that means that in kilogram of gram per kilogram, sorry. So that means in 1 kilogram you have 34.7 gram of salt. In 1 kilogram you have 34 in average. Obviously, around this mean salinity you have huge differences with respect to this mean salinity. We have the Dead Sea, where the temperature, the salinity goes up to 400 grams per kilogram. So that means almost half a kilo of salt in a kilo of water. This is a huge amount of salt. The distribution of the mean is small. Yeah, it's you see that it goes from 1.3 to 3.8 or 36.6, 34.8. This is the 50% of the water is in this range here, but obviously this 400 grams per kilogram in the Dead Sea is also there. But the Dead Sea is a relatively small part of the world ocean, very tiny volume if you compare this with Atlantic or with Pacific or whatever. So you can see that this lower limit of the temperature range is rather close to zero. And in fact, there are parts of the ocean where the temperature is below zero because of the salinity. This water doesn't freeze. Okay, so let's see how the vertical distribution of temperature or profile of temperature looks like, and what is the okay, this is the temperature. This is the Ec2 temperature, what we call it. We didn't remove the influence of the pressure. And obviously what you can, this is from 1,000 meters to 8,000 meters. And we didn't take into account this very surface part. And you can see that the temperature goes from 1,000 meters is like 5 degrees Celsius. And it goes to about 1 degree Celsius. At a certain depth, the temperature starts to increase, the Ec2 temperature. Why it increases? Because the atmosphere, the pressure makes this temperature to increase. And if you use this to calculate the density, what you would obtain? You would obtain that here the density is lower than the density here. But what that would mean? That would mean that the water column is unstable. And water column cannot be unstable. You have the immediate vertical mixing, and therefore there is no. So that's why we introduce the potential temperature, and we do this correction for the atmospheric pressure. And you see now, if you use the potential temperature, you can see that there is no more vertical instability of the water column. And this is one thing. You see, this is what you can see from the density. This is sigma t. The symbol for the density is sigma t or sigma theta, and you can see effectively corresponding to this t vertical temperature distribution, there is equivalent distribution of the density. And you can see that the density here is lower than here, which is not allowed. It's not possible. But only by using the potential temperature for calculation of the potential density, the stability of the water column comes back. And it's really represented. Okay. This is one specific expedition which has been done in 1967, but this is something which can be okay. Well, this one was supposed to be later, but nevertheless I will present to you here. The salinity of the water column of the seawater depends on how much fresh water you put into the ocean and how much fresh water you take from the ocean. You add the fresh water to the ocean by precipitation, so the precipitation and river inflow. You take away the fresh water from the ocean by evaporation. So practically you are decreasing the salinity by adding the fresh water. You are increasing the salinity by taking away the fresh water from the ocean. Therefore, the salinity should depend intimately on the evaporation minus precipitation differences. Evaporation precipitation differences, including also here we have to add the river inflow, river discharge. River discharge has a relatively low contribution because the fresh water from rivers it stays mainly along the borders of the world ocean, and they are relatively small amount of water what is brought by the rivers. If you think of the largest river in the world is having the on the order of 100,000 meter cubic per second is a discharge of these waters. And typical transport, horizontal transport in the ocean is on the order of million meter cubic per second. So at least one order of magnitude is larger horizontal transport in the ocean than the river discharge. So this is how I would define the importance of the rivers into the world ocean. Here, in this graph, what is shown is the again the zonal average all over the ocean of the salinity, this thing dashed line, and you can see that there are two peaks of salinity here around the 50. Around in subtropical areas, and you have a minimum around the equator, another minimum here at mid latitudes. Why is this so? This is because of the evaporation. Because in the equatorial, here these minimum are determined by the precipitation, because you have a lot of precipitation, strong precipitation in the equatorial areas, in the mid-latitude areas. Okay, you have a maximum of the salinity in the areas where the evaporation is large, and it is large in these areas here around 30 degrees north and south, which more or less corresponds to these desert areas. Why desert areas? Desert areas are the areas where the evaporation is much stronger than or evaporation is much stronger than precipitation, or the precipitation is very weak. And so this and desert areas, you will see later, desert areas in the ocean on the land are at the same latitude as we call the desert areas in the ocean, because desert, what that means? Desert means that the biological productivity is low, no plants, no life, or life is very it's very difficult for life to stay there. And the same thing happens in the ocean. And the desertic part of the ocean are the parts where the phytoplankton, the plants are very few, the plant biomass. So, and this is how this looks like, and this is the northern part has another salinity minimum here, and this is where there is a lot of polar ocean in the northern hemisphere, and where is how to say, the ice breaking and a lot of river discharge and so forth, and rainfall. And how it looks like as far as the evaporation minus precipitation is concerned, you can see that the two curves are follow each other rather nicely. Evaporation minus precipitation, that means positive evaporation minus precipitation differences. So evaporation larger than precipitation here and here. And this corresponds more or less to the salinity maximum. Evaporation minus precipitation large negative, which corresponds to the salinity minimum. And so we see how these two curves follow each other very closely. Now, this is what we see if we do the zonal average.
Excuse me.
Yeah,
So we have two questions.
two questions. No, you're right, only one. Tell me.
What could be the reason for the difference between the response in the northern hemisphere, positive 90 and minus 90 this side?
And now we will see the horizontal distribution. This is the average. Or now we will see the horizontal distribution, and we might learn something about from looking at the horizontal distribution over the surface. That's I think one of the next graph will show us. What was your question before we started with lecture?
The question was why was the temperature maximum at around 30?
Why is that?
Why is the temperature maximum around 30 degrees?
Oh, okay. Now we'll see. We'll see also that one. And this is one question. The second?
The second one, there is also a very weird response around 60 degrees. The relation between evaporation and precipitation is low, but salinity is shooting high, around 60.
Around 60. This one here. And here is again something what we should find in the horizontal distribution over the Earth, because here there are some features which you cannot see, you cannot understand why they are if you don't look specifically. Which part of the world ocean contributes to this specific feature? Now let's see. I hope we will see that. I hope I can respond to you. Okay, here it is. Here is the evaporation minus precipitation in millimeter per day calculated from the numerical model, from 40-year average. This is so evaporation minus precipitation. And what we can see here is, first of all, you see around the equator there is the difference is negative, so it means the precipitation is larger than evaporation. This is not perfectly zonal, because there are areas like, for example, along the South American continent, where the entire South American continent is where the precipitation is larger than evaporation. This you can see also here. There are areas where you have the high, very high precipitation. You have to take into consideration that the precipitation, for example, if you are looking at the precipitation, does not depend only on where you are, in which latitude you are. It depends also on the regime of winds, on the orography. If you have, for example, a huge mountain chain, as you have along the Western South American continent, what that means, if you have the winds blowing from the sea, when the wind arrives to the mountain chain, air masses goes up, and then there is a strong condensation and a stronger rainfall. Okay, so this is why, for example, the local conditions, orographic conditions, the wind condition determines the high precipitation here. For example, here is something probably similar, or we are in an area where the wind regime are such that it influences or generates the strong precipitation. But generally, you can see that this is the zonally well distributed. Here you have here, for example, it depends also on, for example, on how warm is the ocean surface. If the ocean surface is warm, what that means, if you have the air coming to over the warm surface, it causes the vertical convection of the air masses. And this vertical convection of air masses creates the formation of clouds and rainfall. So, for example, very likely that here the winds are coming, relatively cold winds are coming over the warm water, and then you got the vertical convection and strong rainfall. So these are the local differences from one area to the other, which then contributes to these features which are different than where the salinity differs from the evaporation minus precipitation. So now your question then was here. We got the evaporation minus precipitation. Here, the salinity was what was that? The salinity was
High.
Was high, is it? Let me see. The salinity was low. The salinity was low, and evaporation minus precipitation was high. Oops. Here, in this part here, if I'm talking this part here, the salinity, the salinity is lower than we would expect looking at evaporation minus precipitation. While here, the salinity is high. The salinity is higher than it would be looking simply at the evaporation minus precipitation. So let's see first what is this around 60 degrees north. Around 60 degrees north we have salinity higher than it would be from evaporation minus precipitation. Okay, let's see. Around 60, which is here. This is 60. Yeah, more or less. Evaporation minus precipitation is the salinity is higher than it would be if it depends on the evaporation minus precipitation. But you know, salinity also depends on the horizontal advection. If you have on the horizontal transport of water, if you have, for some reason, for example here, the bringing of the salty water, the salty water doesn't depend directly on evaporation minus precipitation, but depends also on the horizontal transport. So maybe, I'm saying maybe, there is here the horizontal transport of salty water into this area here, which is more important than the evaporation minus precipitation. So, and I would guess that here you can see that in both area here, this is the North American continent and this is the Asian continent. In both areas you have here the what we call the western boundary current. So this is the Gulf Stream and Kuroshio. These two currents are bringing the warm water from south, but at the same time this water probably is saltier than the water which is present there. So this small thing, the higher salinity, which is not something which we would get looking only at the evaporation minus precipitation, is due to probably is due to the horizontal transport of the salty water from south. Okay. So this is evaporation minus precipitation, but we do have some place. Your second question was considering the temperature. Okay, let's see. Okay, let's go to the temperature, then we will. Yes.
Sir, please, I have one question. Does salinity only depends on the difference between evaporation and temperature? Sorry, evaporation and precipitation. Does salinity only depends on that, or maybe human influences also affects salinity?
Yeah, I mean, prevalently it does depend on evaporation minus precipitation, but in the areas where you have a strong horizontal transport of waters, this can be stronger than the evaporation minus precipitation, but very locally. As we have seen before, the horizontal transport of salty water into the specific area of the 60 degrees belt due to the Gulf Stream and Kuroshio is something which prevails in that specific area, but it's not general feature of the world ocean. It's a very specific feature of the specific area. So, you know, you always have to take into consideration not only the general processes, the large-scale processes, so that means evaporation minus precipitation, but you have to take into consideration that the ocean is not a steel. It moves. It has currents in it. So these currents are very often complicating the situation unless you know what is really the pattern of this circulation, of this current.
Professor,
Yeah.
I also have a question.
Yeah.
About the float of temperature and salinity and precipitation, there is a very low salinity at the north,
Yes.
about 32 ASU. Why is that?
Hey, let's see. That's another. I was hoping that you would not see that. That's the evaporation minus precipitation. I hope that I have the graph which shows the horizontal distribution of the salinity over the world ocean, and we will see exactly why so. No? Because here, for example, if you look at the evaporation minus precipitation, it seems if you do the integral over the entire area, it seems that the evaporation minus precipitation is stronger here than there, because here is around 0, this is -2, and so forth. Why, if we are going to look at if we have, I hope I have, the graph of the horizontal distribution of salinity over the world ocean, I might be able to respond to this question. Okay. Other question? You just remember when we come to this to the horizontal distribution of salinity, then we can analyze why so. What is the vertical distribution of temperature? And the vertical distribution of temperature is something which obviously depends on the source of the heat, because temperature is the measure of the heat content. Therefore, the source of the heat, we know that the heat source is for the sea as the energy coming from the sun. Therefore, logically, the sea surface will be warmer than the deeper layers, and it is so. And what is happening, for example, if you look at the seasonal evolution of the vertical distribution of the temperature, in April, which is this one here, April, which is in the northern hemisphere winter, or late winter, what you can see is that the vertical distribution of temperature is such that there are very small differences between the surface and deep layers, so 0 and 200 meter depth. So you have, like here, you have between 21 and 19 degrees difference. This is obviously the tropical sea, because the temperature of 20 degrees you cannot find here in winter. here you have like around 10 or less than 10. If you go, what is this here? It says January. Okay, more or less. January and April are close to each other, and if you go into summertime, what is happening in the summertime in August? You can see that the sea surface is very warm, and then the temperature more or less goes to the same value as it is during the entire year. What that means? That means that the vertical mixing does not change too much the depth of 200 meters. So the vertical mixing cannot bring the heat from the surface to the depth deeper than 200 meters. And there is so there is this layer here which has a relatively low vertical gradient, which is called also surface mix layer. It's a surface mix layer is because the wind is mixing there the water and mixing also the heat. In September, apparently the wind is more frequent. The calm situations are rare, and therefore the wind mixing becomes more efficient. And the surface mix layer, as a result of that, the energy, the heat, which is here, is distributed vertically, so that you have the surface mix layer reaches about 50 meters. So there is a continuous deepening of the surface mix layer due to the wind mixing. As we go to November, the surface mix layer reaches almost 100 meters, and you have a surface vertical distribution temperature is perfectly constant, perfectly mixed. And then there is this continuous during the entire year, constant temperature in the layer deeper, around 200 meters and deeper. Looking at this thing here, we can distinguish three type of layers as far as the vertical distribution of temperature is concerned. The surface mix layer, where there is a strong influence of the wind. We have the layer of the strong density of a temperature gradient, which is called the thermocline. Let me write down. So there is a thermocline layer. So thermocline is the layer where we have a strong vertical gradient of temperature. And then finally, we have a deep homogeneous layer. Deep homogeneous layer where the vertical mixing does not where the vertical mixing does not come into play, and where the temperature remains constant with that, more or less constant. Obviously, we are always talking in a first approximation constant. So thermocline is the depth where we have a strong vertical gradient of temperature. We have equivalent of vertical gradient of salinity, which is halocline. So that means that the strong vertical gradient of salinity. We have a nutricline. Nutricline, which means that the strong vertical gradient of nutrients. Nutrients are important, you will see later, for the biological productivity. This is the food for ocean plants. So these are the layers where you have the strong vertical gradient of ocean properties in general. Thermocline is strong vertical gradient, of the temperature. So this is the typical distribution of temperature in an area where you have a strong seasonality. So you have what we call a seasonal thermocline. This thermocline appears only during the summertime. In the world ocean and deeper in areas where you don't have a strong summer-winter differences, there you don't have a strong seasonal differences, there is a permanent thermocline. So the thermocline which is always there. And the seasonal thermocline is at a depth on the order of 50 to 100 meters, while the permanent thermocline is at a depth of around 300 meters, 2 to 300 meters in the world ocean. Okay. Now let's see what is the SST, sea surface temperature climatology, for example, for January over the world ocean. These data are based both on satellite observation and ship and buoy observation. So all the measurements, all the sea surface temperature measurements put together, and we did the climatology for January. And what is clearly seen from here is the prevalent zonal distribution of the temperature, which, however, in certain areas is not really perfectly zonal. It's not perfectly zonal because of the circulation in the world ocean, because of the fact that the ocean does parts of this redistribution of the heat in the ocean by itself. So, or vertically or horizontally. For example, where we can see these departures. These departures are, for example, here in general, here on the western coast of South America, where the temperature is lower than it would be if it were only zonally heavy, if it were dependent only on the solar heating. And this is because of the oceanic processes. Here in this specific thing, we are talking about the upwelling. I don't know if you ever heard about the upwelling. Upwelling is the vertical motion of the ocean, or the ocean water masses, which is typically induced by the wind. And why the temperature is there lower than it would be at the same latitude if it were depending also only on solar heating? Because you have the upwelling, so that you have the deeper layer waters which go to the surface. Deeper water layers are characterized by lower temperature, obviously. If you bring them to the surface, then you get the lower temperature, sea surface temperature. And so, whenever you see these blobs of cold water in the coastal area, you can be also almost sure that this is the area of the coastal upwelling. The same thing you might see along the African coast. And so again you see these similar behavior of different oceans, symmetric in a certain sense, because the eastern parts of these oceans, or eastern coast of these oceans, are characterized by the presence of the coastal upwelling. The western part of these oceans is characterized by the western boundary current. So this is the current which goes from the equator toward to polar areas, and you have some signs of these, not very clear signs of these northward transport of the warm water. And the same thing you should be able to see along, for example, the southern hemisphere. But in the southern hemisphere, which are also the manifestation of these western boundary currents, which is in the northern hemisphere, are Kuroshio and Gulf Stream. In the southern hemisphere, you have the eastern Australian currents, which is the boundary current. Which, if you have seen the movie, the cartoon movie, what is the name? Nemo. Yes. Nemo. He was using this. In Nemo, they representing this eastern Australian current, where the guy was using this, was helped by the eastern Australian current to reach Sydney. So so this is these are to a certain extent the symmetricity of the different oceans, both on north and south, and they cause these horizontal transport cause the departures from the zonal distribution of the heat and the temperature. This is the January situation. You see the July and January, see, they are very similar to each other, except for the fact that that during the July is the summer, the northern hemisphere summer, and the southern hemisphere winter, and so simply this central warm area moves north and south in function whether we are in summer or winter, and the signal associated with, for example, this upwelling area along the South American coast and along the African coast is much clearer here, because the wind influences in the southern hemisphere are stronger than this upwelling is stronger, and its imprinting and the sea surface temperature is stronger in this season. The upwelling appears also along the northern American coast. Why it doesn't appears also here? Why it doesn't appear here along the European coast? It depends also on the shape of the coast. If the coast is very steep, if the wind regime is such that it would generate, if the pattern of the quasi-constant wind is such that it would generate the upwelling, the upwelling is present there. We'll be talking about upwelling much more later on, and we'll see what kind of wind we do need in order to generate the upwelling, and how can we predict whether an area would be upwelling favorable area or not. Okay, well, there was a question about the temperature. What was the question?
Why
You forgot. Tell me.
Why are the temperatures maximum around 30 degrees?
Around 30 degrees. This is the 30 degrees, right? This is here. And so we have to combine, what we have to do is that we have to combine summer and winter. We should be able to do the average between this and that. You see, if you look, move this and that, this way and this way, practically this maximum, temperature maximum goes from -30 to +30 more or less. It depends on summer and winter. If you do the average summer and winter, then you would get 2 maximum. You see? Because now if you look at this, oops. Yeah, see? This is the summer, northern hemisphere summer, northern hemisphere winter. See how it moves north and south, and if you do the average of these two, you got 2 maximum. but they are simply due to the fact that you have the seasonal variations. Okay, so it's in this specific case, it's not the question of a horizontal transport. It's the question of the fact that you have a seasonality in the field of temperature. And if you do the average between summer and winter, or over the entire year, you end up with the two maxima in a zonal distribution. Okay. There was another question. You forgot. Salinity.
About low salinity in the.
The low salinity in the northern hemisphere. Okay.
Yes.
With a little patience, I will come to your question also. Do you like this answer? Sure. Even if you don't. Okay, so this is something. This is something which is which gives you an idea how, on a long time scale, how the sea surface temperature changes. This is the sea surface temperature anomaly for January 2005 for a specific year with respect to the long-term climatology. Why is this important? Why is this interesting? This is interesting to see to what extent the situation what we are looking at is different than a climatology. We can do this on a longer time scale and see and find out whether and to what extent the temperature changes for different decades or different years and so forth. So this diagram shows you really to what extent the temperature for January 2005 is differs from the long-term average, and you can see that it goes from these differences can go up to 2 degrees, 3 degrees, and to minus 3 degrees. So this is a pretty large differences in between the long-term average and the specific year temperature. This obviously depends on the specific climatic conditions on the area. For example, generally, what I would say, looking at this picture here, that generally the equatorial area was warmer than the long-term average. So that means that for some reason, and then we should go into more details and find out why this is so. But then the long-term average, the specific year 2005 January was warmer than the long-term average. Or there are some areas like all these around the New Zealand where the sea surface temperature is much lower than usual. See, for example, here along near the eastern African coast and Madagascar, it's much warmer, and so forth. This we can learn a lot by looking at these graphs. We can learn a lot, not only on the climate, we can learn a lot also on what is happening in the ocean. Why is this, for example, in this specific year, equatorial area warmer than the rest of the climatological mean? Then we should have an indicator or indication that something is happening. Then we go back and see a specific, whatever we have available, and see why so. What is really happening? What is process? What causes this kind of departures from the long climatological mean? Obviously, the annual range of temperature is a function of the season. Annual range of sea surface temperature means to what extent, what are the difference between summer and winter, or maximum and minimum temperature over the ocean surface, again sea surface temperature obviously. And you can see that there are areas where you have a huge annual range of the sea surface temperature, which is specifically present in this area here at the same around 45 degrees north. Why is this 45 degrees north? Why this is so? Can we explain this? Certainly not in terms of the solar heating, because these are specific features which are limited in space. They are not zonally distributed. They're present in the northern hemisphere, in a western coast of the northern hemisphere. So obviously it's not that the sunshine is stronger in that area here. There's no way that we can explain this. We have to go and try to explain this in terms of the interior of the ocean. What is happening in the ocean in that specific area, which can help us to explain this annual range? What is happening again? We go back and find out that this is the area where we have the western boundary current. So the western boundary current, for some specific reason, is here in terms of present in terms of the annual range of the sea surface temperature. I would say that this is simply because of the fact that in this area here, the seasonal variability of sea surface temperature is high. What is coming from south by this western boundary current has always the same temperature. And so the difference between the ambient temperature, where this water comes, are larger in winter than in summer. And this is why we have this range, summer-winter range, so big. Around the equator, the summer-winter range, the annual range is the smallest. It's smallest because of the fact that all over the year this solar heating is more or less constant. And you see generally in the mid-latitude areas the annual range is larger than either in polar or in equatorial area. Yes. Okay?
Professor, what about the Mediterranean?
Excuse me?
What about the Mediterranean and the...
What about the Mediterranean? The Mediterranean has a large, it has a large annual range. You see this, the annual range is around more than 10 degrees. Unfortunately, always when they do the map of the world ocean, the Mediterranean is cut in the middle. And, but this is on the order of 10 and 15 degrees Celsius, which is due to the fact that this is a semi-enclosed sea, and it has is surrounded by land. So the annual range on the continent is larger, obviously, than on the ocean, and we have a relatively small water mass present there, and this is why we have the large annual range, which is obviously not the same thing as here. Here you are in the middle of the ocean, far away from the continent, and then your annual range is very, very low. Okay. Here it is. Annual mean salinity. Who was asking for annual mean salinity? Let's see. Why is annual mean sea surface salinity? Okay. What we can see here is the question was that we have salinity lower in this area here than its evaporation minus precipitation. I mean, the salinity is much lower than it would be if our consideration were based only on evaporation minus precipitation. And indeed, you see that there are some parts of this area here where the salinity is very low. Why salinity is very low, I have to disappoint you, but I don't know. in this area. This is the very close to large bay, where you have the ice present, in the presence of ice, which during the summertime obviously is not there. So you have here rather low salinity due to the presence of ice, and which is also the case here and here. And so this is probably the main reason for that. While here in the southern hemisphere around the Antarctic, there is no such pockets of the low salinity water, and therefore the rest of the world ocean, the rest of the world ocean, the salinity is mainly well related to evaporation minus precipitation, except of very northernmost part of the ocean, where in general, but also here, you see, also here the salinity is very low, because you have here the transport of this low salinity water from north toward here. You see what is happening here. You have here on one side you have the Gulf Stream, which flows there, and you have here the high salinity goes over there, and at the same time you have the water flowing from north to south here, and you have a low salinity also in that area here. The coastal form here, Antarctic and the rest, is very smooth with respect to the north, and therefore these pockets of the low salinity water are not, it's not possible to have them. But generally, you can see that their high salinity zonal area is around between 30 and 40, both a little bit more to the south in the northern part. The Mediterranean, you can see the Mediterranean is very reddish, because the salinity in the Mediterranean is higher than the world ocean. Salinity in the Mediterranean is typically between 37 and 38 parts per thousand, or gram per kilogram, while in the rest of the ocean, if you remember, it was like around 25. So the Mediterranean is like a 2 to 3 gram per kilogram more saline than the rest of the world ocean. Similar thing is for the Red Sea and the Persian Gulf, and this, you can see this high salinity water which exits from the Persian Gulf and the Red Sea. This is definitely wrong here, because Black Sea has a relatively low salinity water, but I think it's not very good as for these small areas. And that's it. You have any question for that? Yes.
If there is an ice cover, like sea ice,
Yes.
salinity, surface salinity defined as the salinity of the ice, or
Salinity of the ice is 0.
Yes.
Yeah. So it's
water.
yeah. So it's salinity below the ice cover. Obviously, if it's not permanent ice.
Yes. Because I knew that in regions which where there is ice formation, there is also the process of brine rejection.
Yes. Sure.
So when ice forms, the salts of the
Yeah.
water doesn't get inside the crystals of the ice, so it remains in the ocean. And
Yes.
it should increase the salinity.
Yes.
So
Sure.
that's something which I don't understand.
Yes.
How it kicks.
How come that this is low salinity over there? Because here you have the
Rivers maybe.
rivers, and also the seasonal
Water just from ice,
yeah. And see, yes, you're right that when you have the ice formation, then the salt remains in the seawater, and this is one of the mechanisms how the salinity of the seawater can increase. And but as I told you, these the ice, the permanent the areas permanently covered by ice, that they don't come into this considerations.
Maybe also that the Arctic oceans are very shallow.
What?
It may be also because the Arctic oceans are very shallow in respect to the world ocean.
I don't know how shallow it is on the Arctic Ocean. I must say I don't think it's very shallow. It's shallower than the Atlantic, that's for sure. But it comes 2,000 meters, 2,000 meters, not 2,000, 8,000 meters, I think. So, so it might be. But if you look at this area here, it has a decent salinity, and low salinity is really limited to this relatively coastal area, which has which is seasonally covered by ice or not. So when you have when during the summertime, the water is enriched with fresh water, so the salinity is lower. So generally, these salinity pockets are due to the seasonal presence or not of the ice. Okay, this is one more, and then you're free. This is the. This is how we analyze the for example, the density transect across the different oceans. This is an example of the vertical section of density in the Western Atlantic. So this is from southern to the northern polar areas. And you always have to remember that we have exaggerated the vertical scale 180 times with respect to the horizontal scale in order to see the features, otherwise you wouldn't see anything. And this is the sigma theta, and this is the sigma 4000. So this is just to illustrate you the differences in using the 4000 meters or sigma theta to calculate the density. But this is one thing. The other thing, what I wanted to show you is the general features of the vertical distribution of density. This is Antarctica, and this is Greenland ice and ridge. And what is nice, what is interesting in this graph, what we see here, is that the high density water reaches the surface in the Antarctica, both in the Antarctica, both in Arctic. So that means that there, the areas are where the water is very dense. And not only very dense, but it also seems vertically mixed. There is no differences in density between different layers in those areas here. Why? Because you have the continuous loss of heat in the surface, and this continuous loss of heat in the surface creates the decrease of the water temperature, which then causes the increase of the water density, and then it causes the vertical mixing. So it mixes due to the heat loss, because the sun doesn't bring enough heat in that area. This higher is the loss than the gain. The vertical water column is vertically mixed, and from the surface up to very deep layers. So, which is true both for northern polar areas and the southern polar areas. This is something which is very interesting. You will see later from the point of view of the ocean circulation. Once you go from like a 60 degrees north, or 60 degrees, or 40 degrees, or 50 degrees south, north or south, the thermocline or a pycnocline, I didn't tell you then there is a pycnocline. Pycnocline means the layer of the strong vertical gradient of density, starts to form. This is the vertical pycnocline. You can see the difference between, for example, 5,000 meters and the surface is much larger here than here. So there is no more vertical mixing in this area here. So you have the permanent pycnocline, which then goes to the depth of around 1,000 meters. I told you around 300 meters is 1,000 meters. And then it stays there for the entire year. And then again, when you come to the northern polar areas, again you have the vertically mixed area, and this permanent pycnocline disappears. So you have a kind of north and south. You have the vertically mixed water column. In the middle, you have the permanent thermocline, which separates the surface layer from deeper layers. But not only that. In the very surface area, which is around 100 meters, you have the seasonal thermocline, which is there, which is due to the seasonal variability of the surface solar heating, and so this is the general distribution of the section or the general distribution of the vertical pattern of the density or temperature and salinity. You will see, I hope, later. And so this you will remember this picture, because we will be talking a lot about the global circulation of the ocean, which then can be easily connected to this kind of pattern. Okay. So this is 10:30, and I will